Hello, check. Hello, 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 check. Hello, hello, check. Hi, welcome to this presentation by M. Ashok Kumar. He is currently a faculty at IIT Palakkad. Test. Check, check, test. Yes, so
So anyway, you can edit it out later, right?
desktop audio, everything is up. Should be up on YouTube now.
Not yet. Okay, we're live. Let me- Yeah.
Okay, yeah, so I guess it's on 20 seconds or so.
Somebody,
Okay.
Ashish has joined.
Uh-huh.
Hello, Ashish.
Okay, yeah, so we should be live.
Okay.
Can I start?
So, yeah. Thank you everyone for joining us today for the third part in our Theory Matters Year 1 series. So, we have Shashank also with us, and I'm Amit Alok. And today we have M. Ashok Kumar. So, Ashok is a person well known to both of us. Ashok is basically a mathematician by training. So, he did his bachelor's and master's degree from the Manonmaniam Sundaranar University in Tirunelveli. And after that, he spent a bit of time teaching mathematics, then got interested in applied math and took up a PhD in IISc. After finishing his PhD, and some of the topics he's going to talk about were also things which he got interested in during his PhD. He spent post his PhD sometime at ISI Bangalore as a visiting scientist, and then another stint as a postdoc at Technion. Since 2016, he's been a faculty. He's been an assistant professor first at Indore and his current abode, which is IIT Palakkad. And Ashok today is going to tell us about very interesting problems in information theory on guessing, source coding, and task partitioning. And the underlying object here is Renyi entropies and alpha-Entropies. So we look forward to having an interesting talk with Ashok. Ashok, thank you for joining us, and the floor is yours.
Okay, thank you, Amit, for the introduction, and thank you, Shashank. So I feel this is a great opportunity for all of us to exchange ideas during this lockdown times. So I feel this is great. So this is a talk actually started in IIT Indore with the master's students, this Ashish Thakre, and with my colleague Ashish Kumar at IIT Indore. Then we continued that work with Albert and Dinesh during my time here at IIT Palakkad. So this is this is a talk about these problems on guessing, source coding, and task partitioning, and their deep connection to Renyi entropies. So here is an outline of my talk. So my talk essentially consists of two parts. Actually, the first part is about the various information measures. So I'll be, basically, giving history of these measures. Then I will, in the part two, I will discuss the main problems. Okay, so please feel free to interrupt me at any time. So my objective is to, at least you to learn a bit from here. So it is my objective is not to cover these 19 slides. So yeah, please feel free to interrupt me at any time. Yeah, so I will start from the source coding problem. In a typical source coding problem, we have a set of alphabets, say A1 to A cardinality of X. So I'm not using a new symbol here. So I'm using cardinality of X here. Okay, so and so there is a probability distribution associated with this source, this set of alphabets. So one can think of these probabilities as letter frequencies in a text. So these this set together with this probability distribution is called a source. Okay. So what is a binary code? By a binary code, I mean a string of zeros and ones attached to every letter in the alphabet. Okay. So, for example, we have a source with just 4 alphabets, with A being appearing 50% of the time, B with 25% of the time, and so on. Okay, suppose I assign A to 0, B to 1, 0, C to 1, 1, 0, etc. So this is an example of a binary code. Okay. So for example, the word cab would be encoded as 110010. Okay, so the thing is, the objective in this problem is to encode these letters such that when the text arrives, there won't be any punctuation marks. It would be continuously put down here. So somehow the code words should be in such a way that we should be able to pass them, without any punctuation marks. Given 110010, this one, we should be able to uniquely get back this CAB. Okay, so if we use so with this condition, what is the best way of assigning code words to these letters so that the average code length is as minimum as possible? Okay, so this essentially this corresponds to something called uniquely decodability. So this uniquely decodability is guaranteed by this inequality. So this Kraft-Macmillan inequality says that if the length distributions, so for example, for this code, the length distribution is 1, 2, 3, 3. Okay, so if this length distribution satisfies this inequality, when we raise those lengths to 2 to the minus and sum it over all symbols, it should sum to 1, at most 1. Okay, so this is a necessary and sufficient condition for a code to be uniquely decodable. Okay, so what we want to minimize the code lengths on average subject to this uniquely decodability. So now we have a precise mathematical problem, right? So so therefore the goal is to minimize this expected length L of x subject to this uniquely decodability constraint. Okay, so of course we have one more constraint, that the lengths should be integer values. Okay, so so otherwise this is the optimization problem. So throughout this talk, we would be so this is only so those who are familiar with information theory are very well aware of this source coding problem via this asymptotic equipartition property and so on. And this is also another way to this is an optimization approach. Okay, so we want to minimize this expected length. Okay, so this is summation over x px L of x. So here is so I want to minimize this. So to know that, I would like to know the minimum possible. What is the minimum possible average length? Right? So so I just take this summation px Lx. So I do some modification. I just multiply and divide by px, and I take log and 2 raised to minus L of x, and I have a minus here. So I do some manipulation here. So then what I can do is I can split this into 2. So one is this minus px log px. The other one is summation over x px log 2 raised to minus L of x by p of x. So okay, so I do this in this way for me to get this entropy. So this particular quantity is well known, called Shannon entropy. So now using what is called the log sum inequality. So if we apply this log sum inequality, we would get this. So this would be greater than or equal to summation over x px log summation over x 2 power minus L of x divided by summation over p of x. So summation over x, p of x is 1. So we would get this, actually, it should be minus here. H of p minus log this one. So since this is always less than or equal to 1 by the Kraft inequality, so this would be larger than this. So from this we understand that the minimum possible expected length is entropy. Okay, so this H of p is called the entropy of the source. Okay, so having known this, what would be our next goal? We would like to minimize this expected length, and we now, okay, whatever be the lengths, okay, if the length satisfy this uniquely decodability condition, we have just shown that this is at least entropy. This is at least H of p. So the maximum we can minimize is this entropy of the source, right? So our next goal would obviously be to achieve this, right? So does there exist a length assignment that achieves this? Yes, indeed it is. So it is. So the entropy, the definition of entropy itself suggests that. So if we take this seal, we take the seal so that this is an integer. So this achieves the lower bound. So this is this is an introduction to entropy in some some introduction. Okay, so via this optimization problem, there are many interpretations, many characterizations for entropy, but this is one introduction to entropy. Now a variant of this problem is the following. Suppose the encoder does not know the true underlying distribution P, but he assumes a distribution Q and he starts encoding. Then we know that the optimal lengths, okay, if he thinks that the true underlying distribution is Q, then his length function is going to be log 1 by Q of x. Okay, so but I know that the true underlying distribution is P. So then I calculate, how much expected length he is consuming, right? So I calculate the actual expected length he or she is using. So this is summation over x, p of x log 1 by q of x. So I do this, multiplication and division by p of x. So then I would get this entropy term first, px log px log 1 by p of x plus px log px by qx. Okay, so from this it is very clear that because the encoder does not know the true underlying distribution, he is consuming this many extra bits, okay, per letter, dpq. Okay, so this dpq is this p summation over x, px log px by qx is what is known as relative entropy, or entropy of p relative to q. So which is defined as this px log px by qx. So it essentially has two terms. One is px log px minus px log qx. So in the literature, sometimes the first term is called entropy term. The second one is called a cross entropy term. Okay, so this is sometimes called entropy of p relative to q, because when we take this q to be the uniform distribution, then we would get a constant here and we would get a negative entropy here. So in some sense, this relative entropy is a more general quantity. So in that sense, our Shannon entropy is actually the relative entropy of P relative to the uniform. Okay, so that can be regarded as that way. Okay, so now I have introduced entropy and relative entropies. How do they arise in this simple source coding problem? Okay, so now I am moving to the next measure of information, the Renyi entropy. I'm going to move to the other one. So if there is any question, I can answer now. Okay, so having gotten these two, so entropy was, Shannon entropy was also regarded as a measure of uncertainty. Okay, so there is a vast literature behind this actually. So people have studied it a lot. Why is it a measure of uncertainty? So Shannon himself has in his paper mentioned about this. So according to him, if there is such a measure, say call it h of p1 to pn, it is reasonable to require of it the following properties. So he argued that first of all, it has to be a continuous function. So for a small deviations in the probabilities, there should not be very huge variations in the entropy quantity. So in that sense, it should be a continuous measure. And he also argued that this also has to have this monotonicity property. That is, when all the probability distributions are the when we have the uniform distribution, then this should be a monotone increasing function of n. So this is also intuitively appealing. So this one can always So when the number of symbols actually increases, the uncertainty should definitely increase. Okay, so with the uniform distribution being the case. Okay, so the third one, which is the most very strong property among these three, as far as I understand. Okay, which is called a strong additivity. Okay, so according to him, he says if a choice be broken down into many successive choices, the original h should be the weighted sum of the individual values of h. So that is, if one can think of it as a tree, branching from one. From one there is a branch of 1, 2, etc. n, and so on. So then this entropy of this particular thing should be entropy of in terms of random variables. It is this joint entropy is entropy of x plus entropy of y given x. Okay, so I'm not going very deep into this because this is not the objective of the talk. So but those interested can look into these. Okay, so these three properties actually completely determine Shannon entropy. So if these three properties are satisfied, the measure has to be pi log 1 by pi. Okay, so he in fact in his paper showed that the only quantity that satisfies the above properties is up to a scale factor, constant factor, the entropy. Okay, so yeah, when, as I said, when in the relative entropy, when Q is uniform, relative entropy of P with respect to the uniform is log cardinality of X minus entropy of P. Okay, so since this relative entropy is actually, so from the source coding problem also we know that it is always a non-negative quantity. So h of p is always less than or equal to log cardinality of x. And so from this, Shannon entropy is always at max log cardinality of x. Okay, and is also attained by the uniform distribution. So in some sense, a uniform distribution is the one that has the largest uncertainty. So then, so Renyi, in 1961, came up with this particular quantity. So, he argued that, okay, what is so special about the Shannon entropy? Continuity is fine. Monotonicity is also fine for an uncertainty measure. Strong additivity, he was not convinced. Okay, he argued that in fact, so why do we need strong additivity? Okay, so he just relaxed that strong additivity to additivity. So the joint entropy should be equal to sum of the individual entropies whenever x and y are independent. Okay, so he just replaced the strong additivity by additivity. Okay, so and then he got this family of entropies. Okay, so they are now called Renyi entropy of order alpha. So for every positive number alpha, we have an entropy measure. But this entropy measure is not defined for alpha is equal to 1. Okay, so he proved that these three axioms are satisfied if and only if the measure is either this H alpha or Shannon entropy. Okay, so and one can also show that it is a simple L'Hopital rule that fix the distribution P, let alpha to 1, so you get the Shannon entropy. Okay, so here is an expression where I am trying to understand this measure. This measure px power alpha. So this summation over x px power alpha. You might some of you might recall. If you take a summation over x px power alpha whole power 1 by alpha, then that is the alpha norm. Right? So otherwise, so that is also one thing, and this can be written as px into 1 by px power 1 minus alpha. Okay, so I am just trying to compare with the Shannon entropy. In Shannon entropy, we have px log 1 by px. So instead of log 1 by px, we have some power of 1 by px. Okay, and then whole raised to the power 1 by 1 minus alpha, and then a log. Okay, so this is a small interpretation from my side. Okay, so there may be some other nice interpretations, but this actually, it was purely a mathematical paper. It was purely from a mathematical point of view. So what will these axioms yield? Okay, that was his question. So Renyi was a purely a mathematician, probabilities. So his thing was if I replace this strong additivity by additivity, what would I get? So that work involved all these functional equations, etc. And he finally arrived at this particular quantity. I don't think in his paper he gave any interpretations from these expressions. I'm not sure. Okay, so this is how we arrive at Renyi entropy. Okay, so then what is the usual natural question? So from an engineer's point of view or a scientist's point of view, okay, we have gotten some quantity. Okay, so is this useful for something? Right, so people actually at that time, as soon as they came to know this, people wondered whether there is any application of this. Okay, is this related to something? So Campbell came up with a problem. Okay, so he said, if we actually minimize the exponentiated lengths, actually, so in the Shannon's source coding problem, what we minimized was this expected lengths E of L of x. Instead, if we minimize this, so you exponentiate this E raised to rho L of x. Okay, take expectation, then take a log, then normalize by this this row. Okay, so this is sometimes called cumulants. Okay, so these are called, so this is moment generating, this is expectation of 2 power rho L of x is our usual moment generating function. So logarithm of this is called sometimes cumulants, and you divide by rho, so it is called normalized cumulants actually. So here again, here again Campbell was also not okay. He didn't tell what is this useful for, but he just tried. So but because as of now we don't have any problem associated with Renyi entropy. Okay, so any engineering problem associated with that. So but Campbell was able to do only this much. So he says, instead of expected length, if you for some reason if you want to minimize this one, then what you so what you get is actually the optimal one. I will come to that. So he considered these, but later actually Weiner in 74, actually Campbell was around 64 or so. Okay, so he actually proved that in fact in sources with buffer overflow, that is, there is actually I don't work in this area, but I know a bit on this. So only thing is, there is something called sources with buffer overflow. Okay, so suppose the rate at which the input symbols are transmitted is higher than the rate at which the symbols are encoded. So then there will always be overflow. Okay, so there will be a buffer and that might overflow, and one needs to minimize also this probability of buffer overflow. Okay, so he in fact proved that this particular quantity is what we need to minimize. Okay, so for an appropriate row. Okay, so Weiner in fact proved that in such source coding problems one needs to minimize this cumulants for an appropriate row. Okay, so that is another story. Okay, so Campbell.
Ashok,
Yes.
one question.
Yeah.
Here in this optimization problem, there is no constraint like your Crafts inequality or.
Yeah. We have.
Okay.
So this, very good. Good that you asked. Okay. So yeah. So here again, so the objective function is the only change. But the constraint is overall uniquely decodable codes. Overall uniquely decodable codes, that is equivalent to Kraft inequality. Okay. So only the objective function changes. Okay. So he actually proved that the minimum cumulant is Renyi entropy, okay, of order alpha, where alpha is this 1 by 1 plus rho, this cumulant exponent rho. Okay, so this is the connection between alpha and rho. Okay, Campbell was in fact 65. So we know that, this is another interesting thing, So in the Shannon source coding problem, the optimal code lengths were, log 1 by P of X. But here, it is log 1 by P alpha of X, where this P alpha of X is called an escort measure or an alpha scaled measure. Okay, so this measure actually comes in several places actually. So there is something called non-extensive statistical physics, etc. So there is this Renyi entropy also applied in statistical problems, inference problems, where somehow this alpha factor arises there as a robust parameter. Okay, so that community calls this particular distribution, this P alpha of X, as an escort measure of P. Okay, so here we call alpha scaled measure. So what would be the natural question next?
Ashok, I have one question.
Yes.
Yeah, so in the previous slide, you had this third axiom for the Renyi entropy, right?
Yes.
So suppose you did not have that independence between x and y. So I suppose that alpha would turn up in the expression, correct?
Yes, yes. Yes.
So does that give you any meaning at all?
That's a good question. Yeah. So that there is a paper by Cesar actually. So where actually, in fact, he defines joint entropy, etc., based on Renyi entropy. Okay. So that paper, the title is Generalized Cutoff Rates, etc. I can forward that. So that is another yeah, that is in the channel side.
Right,
So
exactly.
Renyi entropy arises there also. So in this talk I'm completely concentrating on the source coding part, but that is also a very interesting paper, really. So where he actually defines this mutual information, etc., based on this Renyi entropy also.
Okay.
Thank you. Yeah. So the next natural question is the mismatched case, right? So there it was Shannon entropy plus relative entropy. Now, so what is that? Okay, so now we have a big expression. Okay, so in the mismatched case, that is, suppose the true underlying distribution is P, but we do not know that, and we do this coding, but we are minimizing the cumulants only. So then the optimal cumulant is Renyi entropy plus this measure I alpha PQ. So where I alpha PQ is given by this big expression. And so here also, this can be, the first term can be interpreted as P log 1 by Q, or P log, okay, minus P log Q. Okay, so this is the one, this is a term corresponding to that, and we have an entropy term. Okay, so actually this particular quantity was first studied by Sundaresan in his 2002 ISIT one, actually. So, but even before that, Bloomer and McCallies studied the Huffman coding part of this particular problem, but they do not have they studied the redundancy, etc., in this Campbell's problem, but they do not have a expression of, they did not find the the redundancy exactly. Okay, so yeah, so this actually Sundaresan called it an alpha entropy of P relative to Q, and recently people have started using the name Sundaresan's divergence. So as relative entropy, this measure also is also non-negative and is zero if and only if P is equal to Q. So the same property enjoyed by relative entropy. Okay, as we expected, so as so again, like Renyi entropy, this also cannot be defined for alpha is equal to 1, but one can talk about alpha tending to 1. Okay, so fix P and Q and let alpha to 1. Okay, so then you get your relative entropy or the Kullback-Leibler divergence. Okay, so yeah, so as so again, right, like Renyi entropy, so I'm this done with the first part. Okay, so far what I have done is I have just introduced these measures, Shannon and Renyi measures. Okay, so how do they arise in this source coding problem? Okay, so if there is no question, I can move to the, yeah, we can pause for a few seconds and we can move to the next part. Yes. Yeah. Oh. Yeah, actually, people have done that actually, but I did not see any merit in that actually. I did not see any merit in the sense, see here these measures arise quite naturally, so I have seen some generalizations where there was no proper meaning to the, generalization, even whether mathematical or operational. So, yeah. So I haven't seen. I don't remember. Yeah. Yes. Yes. Yeah. Yeah. Yes. 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 Yeah. Yeah. So there are some channel coding problems also where, Renyi entropy and yeah. At this point of time, there is one more thing, in that in that paper by Renyi, actually there is he also proposed a divergence quantity, relative entropy quantity, which is different from this I alpha measure actually. So that is now called Renyi divergence.
Sure.
Okay.
Yes.
Yeah. So, but the thing is, although this I alpha divergence, this Sundaresan's divergence, is closely related to Renyi divergence, but both are not the same actually.
So
there, but
where does the Renyi divergence arise? I mean, it's
yeah. So Renyi divergence arise in some channel coding problem of Chiza. So that I don't know what is it, but that is something nice paper, I think. So it appeared in TIT. It is the title is something like generalized cutoff rates and there any information measures, something like that. Okay, so appeared in IEEE transactions on information theory.
okay.
Okay, yeah. So yeah, so I will now move to the other problems where any entropy is very much related. So the guessing problem. So where we have we have a set of objects. We have a set of objects. So Bob thinks of an object from this. Some random object from this X, and Alice has to guess it. Okay, so but the condition is that she can ask only questions of the form: is X A? Okay, is X A1? Is X A3? Etc. Okay, so she cannot ask questions like okay, in this particular problem. This is a problem studied by Massey and Arikan. So yeah, so the question should be of these problems of this type only. Is X A3? Is X A5? Etc. Okay, so this was studied by Massey and Arikan. This has got several applications. Okay, so let us let us define a function gx. Okay, gx is the number of guesses required for Alice to guess X correctly. Okay, so number of guesses required for Alice, gx. So then our goal is to minimize this expected number of guesses, right? So one is interested in minimizing the number of expected guesses over all guessing strategies, right? So yeah, so this is a problem. So essentially, mathematically, a guessing strategy.
Just a question. So,
Yes.
So you have to guess it exactly, or is there like a probability of error associated with it?
Exactly.
Like you have to guess.
Yeah.
Oh,
So,
exact guess.
yeah, one has to guess it exactly. you ask, whether is it A1, A2, etc. In some order, So yeah, so that order is essentially this G. Okay, so G is essentially an one-to-one mapping from this set of objects to the numbers 1, 2, etc. cardinality of X. Okay, so yeah, so this is the
Sorry, one more question. So
yes.
the strategy G is fixed beforehand, or like you can, like it can be interactive, like depending on the answer you can choose your
Yeah. So depending on the answer, only you are going to ask the next guess, right?
okay.
So if the answer is once the answer is yes, you stop. Okay. So Bob has thought of an object. Okay, say A5. You ask, is it A7? He would say no. Is it A9? He would say no. Is it A3? No. Is it A5? Yes. Done. So number of guesses required is 4 or 5. Okay. So yeah. So this is the problem.
Ashok, Amit Alok here. So just to clarify the point by Manoj. So a guessing strategy could be the following as well, right? It can be a static assignment where for every X, I just tell you the order of what is the sort of questions I'm going to ask. So Bob will fix this upfront. And am I not, in some sense, minimizing this possible assignment? So for every X, Gx is basically a list of questions. I don't understand. So I'm a little so is Bob depending on the answer? Is it like an adaptive thing where Bob looks at the answer and then puts out the next thing, or is it a strategy which is fixed upfront and then the routine just runs and verifies it?
So
Yeah, exactly. This was my question.
Yeah, so Alice actually, So the G is with Alice, So she can, she asks questions according to the answers, earlier answers. She would stop once the answer is yes.
Okay. Yeah, maybe I'll come back to this question. Perhaps. Yeah, sure. Yeah,
so for example, you can you can assign. So there are several. I don't know the exact number, but so you may suppose you have say 3-4 objects A, B, C, D. So you may ask in this way. How many possibilities are there? Cardinality of.
So it's basically 4 questions I ask, right? So can I define my strategy upfront, or can I do it like adaptively, where I ask the first question, so I only tell you the first guess that I'll have, and based on that answer, I could maybe pick something.
Yes.
Oh,
yeah. So actually, both are same. Actually,
Oh yeah, that was actually the question. I was wondering if both are the same or they're kind of different.
Yes.
Okay. Fine.
Yeah.
I mean, I guess the strategy for non-adaptive strategy would be just to ask questions in the order of decreasing probability, right?
Yeah. So I'll come to that. So here also, I missed this. So there is a probability distribution also associated with this set X. Okay. So what is the frequency with respect to which Bob can think of one of these objects? Okay, so there is a probability distribution associated with this. Okay, so as Shashank said, this is quite natural that if Alice knows that distribution, then her optimal thing would be to guess according to the decreasing order of these probabilities, right? So if A1 has got a larger probability of Bob thinking of it, then her first question would be, is it A1? Okay. So if Alice knows the underlying distribution with respect to which Bob thinks of these objects. Okay. So yeah, so this problem was studied by Arikan, and so Arikan gave this lower bound. Okay, so actually, this problem also can be thought of as this problem also can be thought of as the coding problem, right? There we had expected L of x, E of L of x over all length functions. Here we are minimizing these over all guessing strategies. Okay, so all guessing functions. Okay, so
I guess, I mean, the source coding problem, we're allowing arbitrary questions, right? Whereas here we're only allowing specific questions.
Yes, yeah, there is some, certainly, yeah, there is some, so here, so the guessing strategy would satisfy this property. That is, for a guessing strategy, this sum will be the same, right? 1 plus 1 by 2 plus etc. This, whereas okay, so but not everything that satisfies this will be a guessing function. Okay, whereas in the coding problem, so if a length sequence satisfies the Kraft inequality, then that would also be a uniquely decodable code. Okay, so that is a bit difference, but yeah, I will come to that, but it is not a big problem actually in this optimization problem. Okay, so he also proved that there exists an optimal G star that achieves this one. So where this H 1 by 2 of P is any entropy of order half. Okay. So yeah, so what is the guessing strategy? The guessing strategy that achieves this bound is not actually P. Okay, although, yeah, as Shashank said, you don't need, you just need to know the underlying probability distribution, and that is your optimal strategy. You go according to the decreasing order of probabilities. But the one that attains this optimal value is not P. Okay, but not okay. That obtains so that the optimal G star is not in terms of B, but it is in terms of square root of P. Okay, so that is an interesting observation which is useful in the next two problem. Okay, so yeah, so they have this result for an n-length sequence also. So in the long run, we can in fact achieve exactly the Renyi entropy. Okay.
Oh, so here instead of the guessing, you're not trying to minimize the expected value of the guess number, but some roth power of the guess number.
Yes. Thank you. Yeah, thank you for asking this. Yeah. So this problem actually can be generalized to any roth moment. So here rho was 1. Okay, when rho was 1, it was 1 by 2. Renyi entropy of order half. So when it is actually roth moment, then it is Renyi entropy of order alpha, where alpha is 1 by 1 plus rho. So when rho is 1, it is 1 by 2. Okay. So yeah, this if someone is if someone is interested in the second moment, third moment, etc., one can have this. So and one can also show that the interesting thing is, again, in the mismatched version, suppose you do not know the underlying distribution and you guess according to another distribution Q, then again the penalty is this, this divergence I alpha PQ. So that is another, again, interesting thing. So now we have seen, two problems where this pair comes, Renyi entropy and relative alpha entropy. Okay, so the third problem is the memoryless guessing. Okay, so it was yes.
So since you're trying to go back from like these quantities and map them to some operational values, just a thought here. So for these guessing problems and the source compression problem, right?
Yeah.
Are there equivalent objects if, for example, you go from source coding to rate distortion? Like, is there, instead of, like, I think Manoj or I think somebody asked earlier, so instead of maybe wanting to guess exactly, if I instead ask that I want to put a distortion measure like we do in source coding, dx comma x hat and say I don't want to guess exactly, but I want to guess within some distortion, like we do in source compression. Is there like an immediate operational point? I mean, a quantity like H alpha or some version of it?
Yeah, this is a good question actually. Yeah, so I don't know of this for the guessing problem, but this has been done for the task partitioning problem I'm going to talk about. Okay.
Oh, okay.
So, but this one I am not aware of. I don't know. Somebody has done it. Yeah. Yeah.
Okay. Thanks.
Yeah. So this is a variant of Arikan's problem actually. This memoryless guessing. Okay. So it was reported recently in the 2017 ISIT. So here the difference here from the earlier guessing problem is that, so the Alice, you can think of Alice as a machine, memoryless one, so she can ask the same question again and again, so it is in some sense automated fashion. Okay, so the machine will just generate a sequence of independent guesses, x1 hat, x2 hat, according to some distribution, because Alice does not know. Suppose Alice does not know that, even if Alice knows the distribution, it doesn't matter. Okay, so suppose the machine thinks of guesses independently every time according to some distribution p hat. Okay, then what is that we are interested in? Suppose x is the one that Bob thinks of, then so when would she guess it correctly? Okay, so what is the minimum case? It's that x, so she does an independent guesses, and so what is the k for which this is equal, minimum k. So this is the guessing function now. Okay, and these guys looked at what is known as this factorial function instead of that Roth moment. So what these Huieihel et al. Studied was this factorial moment, expected value of this v rho of x. Okay, so this is essentially g of x into g of x plus 1, g of x plus 2, etc. Okay, so when rho is 2, then g of x plus 1 by 2 factorial, etc. Okay, so when rho is equal to 1, it is essentially the this is just g of x. So then we have expected value of g of x. Okay, so at least so I do not know what is this function useful for, but I have seen this particular function in other mathematical works, but in terms of applications I don't know, except yeah. So but the thing is, yeah, in a higher order values, when rho is equal to 2, etc., second moments, etc., will occur. Okay, so but at least when rho is equal to 1, it is the expected value. Okay, so but interestingly, they also found that this particular factorial moment is actually expected value of 1 by p hat of x power rho. Okay, so this is something interesting actually. So when I saw this work first, really I was fascinated, because I kept on seeing this kind of problems, so where everywhere, even in the source coding problem, in the Campbell's problem, you have something like expected value of e raised to rho L of x. Okay, or expected value of 2 raised to rho L of x. So, and in the guessing problem, and now in the memoryless guessing problem also. So initially I thought, this is some factorial function, but when we calculate this expected value, it turns out to be some Roth moment of something. Okay, so then see here, what is the problem? We need to minimize this. We need to minimize this factorial moment, subject to the constraint that this p hat is a probability measure, right? So that is, so because you have to minimize this over all p hats, right? You have to minimize this over all p hats. So, but p hat is a probability measure, that is sum is 1. So the constraint is sum over x, p hat of x is equal to 1. So again, this problem also falls in that framework. Okay. So yes, again, so they also proved that this minimum factorial moment is given in terms of Renyi entropy
So
of order. Yeah.
Shashank,
Yeah.
sorry to interrupt. So is there
Yes.
any other application of this memoryless guessing problem?
Yeah. So there are works recently, by the same authors or some authors with some intersection, So which I do not know exactly. There are some recent works based on this memoryless guessing. Why botnets work, etc. So there is some paper appeared in transactions on information. What is that? There is one more journal, right?
Forensics and
Forensics
security.
and security.
Yes. Okay, yeah. So that is very recent. I think 2019 or 20.
Okay.
Some of our students also do memoryless guessing.
Okay. So again, interesting thing is, see, again in this problem also, in the mismatch case, again this same pair, or any entropy plus this Sundaresan's divergence. That is another interesting thing. Yeah, so I'll talk about the last problem, task partitioning problem, actually. So I hope I'm exceeding time, but so pardon me for another 5 minutes.
It's okay. We started late, so go ahead.
It's okay. Yeah. Okay. Thank you. So again, in task partitioning problem also we have a set of tasks. So like a set of so alphabet set, etc. Set of objects, etc. Now we have a set of objects. Okay. So, and probability distribution associated with this set that can be thought of as, frequency of occurrences of the tasks. So now the problem is this cardinality of x tasks are to be assigned to m keys. Okay, where m is strictly less than this number of tasks. Okay, so one can think of, you can think of this as a, kind of robot. Okay, so this is something that we used to think, but you can think of like a robot, so that is supposed to do all these tasks. The robot has only, say, so we have 6 tasks, but there are only 4 keys. Okay, so these 6 tasks have to be assigned to these 4 tasks. Okay, 4 keys. Okay, so obviously some key would receive more than a task. Okay, so now, okay, so the task may be clean the vessels, do so the tasks also have varied frequency of occurrence, right? Like do a haircut, so that appears not quite often, right? So but so something like this. But the thing is, suppose I want to do a haircut, then I will press the key associated with that task. But because more than one task may be assigned to that key, so this machine will actually perform that unnecessary task also. So this is the problem. We need to minimize this as much as possible. So we need to minimize this redundancy as much as possible. Okay, so how are we going to, this is then essentially this is so this is not, by the way, this is not the way this problem is stated in Bunte and Lapidoth, but for the sake of it is it is written from a coding point of view, but essentially the problems are the same. Okay, so yeah, so essentially for the m keys we need to,
Ashok,
yes,
sorry to interrupt.
Yeah. Yes.
Just trying to understand the problem. So you
Yeah.
have a bunch of tasks,
Yes.
and you can assign multiple tasks to a single key.
Yes.
You have fewer number of keys than tasks.
Yes.
If you press a key, then all the tasks associated with that key are executed. Is that it? Or no?
Yes. Yes. So I didn't mention that. Yeah.
Okay,
Yeah.
so if
Yeah,
you
that
press
is
that key,
yes,
then,
yes,
then
you're right.
all those tasks are executed.
Yes. Yeah. If
And
if the number of keys is cardinality of X, then there is no problem in it. You press the
correct.
key that you want
Sure.
to
Sure.
press, then your task is performed. Now, because of this, non-availability of sufficient number of keys, more than one task, more than one task than the intended task will be performed, right? So
And you want to minimize the number of tasks that is performed by a single key? Is that right?
yes, exactly. On average,
Okay,
on
yeah,
average.
depending on whatever metric you.
Yes. There is a probability distribution. There is a frequency of occurrences, right? Somehow, no. This is essentially how are you going to partition that task into partition of size m,
Okay.
right?
Fine.
Because there are only m keys. Okay. So this is essentially you have a partition of X of size m. So there are so many ways by which you can partition, and which partition will give you the minimum expected number of tasks performed, right? Yes. So the goal is to minimize this expected value over all partitions, overall possible partitions. See, here again, actually, this problem also falls in the other category, really. Expected, minimize expected length, subject to what is the constraint? Subject to, the partition, overall partitions. So an interesting thing about these partitions is that, if you sum over all X and, where Lx is Lx is the partition function. Okay, like the guessing function, here we have partition function. So there, if you sum 1 by g of X, you would get that harmonic sum. But here, this is a very simple, this is an interesting observation that if you sum over all X 1 by L of X is the cardinality. Okay, so it should be cardinality of L of X. Okay. So L of X is the subset containing X in the partition. Okay, so what will happen is, so for all those X in that particular subset, it is going to be same thing, right? 1 by cardinality of that, so that many number of times. So it is a very simple exercise that you can show that this is exactly m, that partition size. Okay, so again, so it doesn't mean, okay, suppose I have a partition function that satisfies this, that is equal to m. The reverse is not true. That is, it will not lead me to a partition. Okay, although a partition satisfies this, so that is the difference from our source coding problem. Source coding problem there is very tight. A code is uniquely decodable if and only if the Kraft inequality is satisfied. So this is the analog of Kraft inequality actually. Okay, this is the analog of Kraft inequality, but not it is not very strict. There is no if and only if. Okay, so that is the only difference. Okay, so here again, they showed that they found that this moment, Roth moment is bounded below by Renyi entropy, and this log m is the number of keys available. And interestingly, they showed that this is what we want, right? 1. See, that I would be more happy when my intended task is performed in one shot, right? So that is possible in the long run. They proved that if your partition size is, or the number of keys is in such a way that log m is greater than Renyi entropy, then this is true. And if it is less, then in the long run, it is going to be infinity. Okay, so this result is there. Again, the interesting thing is the optimal one, the optimal L star that attains this is actually based on the alpha scaled measure I was talking about, right? Escort measure by the physicist, So this is again, this is something interesting. Yes,
yeah,
yes.
Sorry to interrupt again.
Yes.
So how does I mean, yeah, you should for in the two conditions, if log m is greater than h alpha of p and log m less than h alpha of p.
Yes.
So p is a function of n, right?
P is a function of n. Which n?
So p is a probability distribution on x1 through xn, right?
No, P is a probability distribution on these symbols only.
It's the
So
IID
then,
method.
yeah,
Oh.
yeah, IID, yes, IID case. So here, yeah, you are right. Okay, so your confusion is very reasonable. So yeah, when I talk about this measure, I'm talking about the product distribution.
So then the log. Okay, fine.
Yeah. Okay.
And Ashok, one question here. So the alpha is given as 1 upon 1 plus rho, like it was earlier.
Yes. Again, yes. Again, the same.
Okay.
Same thing. Yes. Yeah. So, in fact, actually, even in 2011 itself, Manjesh Kumar Hanawal and Sundaresan, they in their paper also they brought out this connection between source coding and guessing problem at that time. But then after seeing several such problems, we thought of finding the deep connection between these problems. So yes. So then so in this process, we also thought about a more general task partitioning problem. So in the task partitioning problem of Bunte and Lapidoth, what happens is, every time a key is pressed, all the tasks associated with that key are performed, right? So suppose now we assume that there is a genie, so that would stop it once the intended task is performed. What is the point of performing all the tasks? So so once the appropriate key is pressed, all the tasks starting from the of course it should start from the most frequent ones. So it will stop when the intended task is performed. Okay, so we considered this problem.
Sorry to interrupt.
Yes.
So what's the ordering of tasks within a single key? Because I think
good question. Yes, good question. So so here actually one can show that it is very simple, really. If you take any other order, the expected value will be larger only. So it has to go the optimal one. So you can show that the optimal one will go again decreasing order of probabilities in that particular subset. Okay. Yes, very good. Yes, correct. Yes. So then here, that is why we define this n of x with the number of tasks until and including x. Okay. So then actually, you can see that so in the usual task partitioning problem, this sum was just m. Okay, but here though this will be something like this. Okay, but interestingly, this can be shown to be, so one needs to use a a bound by logarithm here for each of these terms, and then you just need to use a AMGM inequality, and you get something like this. So it is. So you can see that this is actually this problem is actually a generalization of not only the Bunte and Lapidoth's task problem, but also the guessing problem, really. If you see because so for the guessing problem, your m is just 1, right? your M is going to be just 1. There is the partition is the trivial partition. Okay, the partition consisting of all the objects. Okay, all the tasks. Okay, so that will be, then you have this order also. You are going to stop the task once it is performed. So in the guessing problem also, you are going to stop once Bob says yes, right? So this problem actually is generalization of both Bunte and Lapidoth's task problem as well as Arikan's guessing problem, really. Okay, so the optimization problem, underlying in this problem is this, minimize this row moment of this subject to this. Again, by now it is not surprising that again, Renyi entropy and Sundaresan's divergence come in the optimal solutions. Okay. So yeah, this is what we thought that, so all these problems actually fall in this framework actually. So you want to minimize something, an object of this form, 1 by rho log expectation of phi of x power rho, satisfying the constraint that, so here phi of x power rho, in the constraint it is 1 by phi of x. Okay, summation over x, 1 by phi of x less than or equal to some constant. In the guessing problem, it was, so phi of x was 2 raised to L of x. 2 raised to L of x, b was 1. Okay, so similarly, all the other problems, you can find out the corresponding b, and you can cast those problems also in this framework. And we in fact showed that, so this is always bounded by, the interesting thing is, this is independent of this phi. Okay, so it so the lower bound is given by this, and is also achieved by that alpha scaled measure.
So okay. Ashok, here there is no assumption on phi, like no convexity requirement or anything like that.
No convexity, because you see the optimization is over phi, and the function, the underlying function is actually power rho, right?
Yes.
Okay, it is like x power rho. The underlying, actually, yeah, you are right. The problem is convex problem only actually here, because your optimization is not over x but phi.
Oh,
okay.
Right. Okay.
Yeah,
okay.
Phi is like an n-dimensional vector, and so your underlying function is actually x to the power rho, and because you have this 1 by rho, etc. This problem actually, I'm going to say exactly that. Actually, I'm going to use same technique. You remember, right? In my first second slide, I used to find the lower bound on the expected code length by the Shannon entropy, right? I use the log sum inequality.
Yeah.
Here I'm going to use the generalized log sum inequality. The proof is just one line. Proof is just by the generalized log sum inequality applied to this function x to the power minus rho. So this is the object of interest, that is expected value of phi of x power rho, right? P of x, phi of x power rho. So I can do this this manipulation. If you simplify, this is exactly equal to this actually. So I'm writing this because I want this summation ai bi by ai, right? Ai some convex function of bi by ai, right? So that is why I write it like this. Then by generalized log sum inequality, this is this, and just you take then log and then divide by rho, you get exactly this, and you use this thing also, this constraint, right? Summation over x, phi of x power minus 1 is less than or equal to b, then you would get this. Okay, so yeah, so that is essentially
so Ashok, question
yes.
here. So
Yes.
for the n letter random variable, what is phi? It's the product of phi of xi.
So phi is some function of. So in the guessing problem, it will be you are going to guess a sequence of objects, right?
Yes.
So the problem would be taken to the n dimensions.
Correct.
So phi of x can be the length function, or the guessing function, or the part.
So what is phi of xn in terms of phi of x? Is phi of xn equal to sum of phi of x?
No, not necessarily. No. Yeah, not necessarily. Because see, phi of x here in this problem, the phi of xn is this ln of xn, right? So
correct. So
the same problem is taken to the n dimensions. So you are
number, right? So the phi, even for a vector, it's basically going to represent it as a number in terms of bits or in terms of just natural numbers. Isn't that the mapping?
Yes, exactly.
It will be just number from 1 to the size of the number of xn's.
Yeah. So here when it is for n is equal to 2, so the my underlying alphabet set is going to be that script x power 2, Cartesian product of x itself with itself.
Yes.
Okay. So then the number of keys will be how many? That cardinality of x square. That many keys, and that many keys are available. That many tasks are available.
Yes.
And how many m square keys are available, and so on. Is that clear?
So,
not exactly. Huh?
Not fully.
Yeah. See, so let's take the 4 tasks. Okay, A, B, C, D.
Sure.
Okay. So in 2 dimensions, your problem is going to be the available tasks are actually AA, AB, AC, etc.
True. Yeah.
X cross X. Correct. That is going to be your task set.
Fine. Yeah.
Okay. And the number of keys. So if there are 2 keys available when n is equal to 1, then the number of keys is 4 now.
Sure.
So again the same problem. You have now how many 16 tasks and 4 keys.
Sure.
Okay, so when n is equal to 3, so the same.
Okay.
Yeah. You understand?
But, okay. Can you go to the next slide once again?
The last one.
Yeah, this is fine. Yeah. So maybe what I'm not able to understand is what is phi here.
So this is a general mathematical problem. Okay. So what we are trying to say is that those
fine. Yeah,
you understand?
Wait. So okay.
Yeah. So we are trying to say is that all the problems studied, whether it is source coding problem, or the guessing problem, or the memoryless guessing problem, or the task partitioning problem, or the generalized task partitioning problem. So all those problems essentially lie in this particular framework for some appropriate phi. For some appropriate phi, so everywhere the same, because phi is a dummy variable, right?
Sure.
What is in every problem? What is going to change is this b only.
Yes.
Okay. So, but the thing is, in source coding problem, you don't allow all the phi, but only those length functions only you are allowing actually.
Sure.
So, but so in that sense, if that is also the case, then all the problems are. So our final as of now, our understanding is that all the problems are different, though. There is a deep connection, so even in 2011 itself, Hanawal and Sundaresan proved that there is a deep they showed that there is a deep connection between the Campbell's problem and the Arikan's guessing problem, saying that you don't need to know the true source. Okay, you don't need to know that. So suppose you have a source and you give me the optimal length function. Okay, you give me the optimal length function. I can give you the guessing function, optimal guessing function. Okay, and vice versa. Okay, so I don't need to know the true source actually. If you give me for that problem, because for both problems the source is same, right? The source is same. Suppose you know the source and you give me the optimal length function, I can immediately give you the optimal guessing function.
Yes.
And the reverse is also true. That is what they proved actually. But the same thing we don't think that can be proven for the other problems, although but mathematically there is all the problems somehow all the problems can be solved. That is our argument. All the problems can be solved from this single result. Not the mismatched version, but the other one. When the true distribution is known case. All the problem from this single theorem, all the problems results can be established actually.
Yeah. So
Okay.
I mean, the way you're stating this, it's just it's just an optimization problem, right?
Yes,
it doesn't really
yes.
tell you about the sort of a coding scheme.
Yes.
You're not connecting any sort of a coding scheme with
Coding
this theorem.
scheme, yeah, this is it is indeed saying, right? So the optimal one, that is, it is achieved by this one. So that was evident, right? In all the problems, it was evident that the optimal solution was in terms of this.
Correct, but here you're not really giving an interpretation of what phi is. So for example, in the context of source coding, a theorem of this form would tell you what the lengths are, right? But it doesn't tell you what the code words are per se.
Yes, of course.
So similarly, it's
Yes, of course. Yes. Yeah, that's it. Any further questions?
Any questions? We've been asking quite a few, so
Just a quick comment.
Yes.
So there seems to be some obvious relationship between this task partitioning problem and collision-free hashing.
Oh.
I don't know if you have thought about it in that way, because it's almost the same problem is what I see. Only
yeah,
that
I agree.
Collision free? What is it?
You just have some items and you're trying to store them or store them in an optimal way or something like that, recover so that you can recover them.
Yes.
And you compute some hashes, low length hashes for each one of those items, so that when you want to recover the items, you go for the hashes first, right? And the hashes tell you where the items are or something like that. Right? And you don't want collisions to happen, and therefore you have to choose your hash functions in an appropriate way, right? So
actually, collision probability is really the Renyi entropy of order 2, right? That's how you define, because it's the expected. Expected P of X, or
that
I mean, it's the probability of X being probability summation Px squared, right? That's X is equal to X prime is equal to X. So
okay,
that is, I think.
Yeah, in fact, when here, when Roth moment, when rho is equal to 1, the optimal solution would be, because H alpha is 1 by 1 plus rho, right? So it is going to be, alpha is going to be half when rho is 1.
Yeah,
maybe that is why it is called. Renyi entropy of order half is called collision entropy, right?
I think order 2 most likely.
Order 2, huh? Okay, yeah.
Okay, actually, I'm not sure how. Maybe that. I remember, some expectation P of X is really the Renyi entropy. So that would be, maybe in your notation it is order half.
Okay.
Any other
Thanks.
question? Thanks, sir. Yeah, any connection? My question again. Sorry to hog the time, but any connections to the channel coding problems? Like even I know you mentioned that there was some work by Cesar, but like, is there an obvious occurrence of any channel coding problems that you know of?
No. So I know of only that particular paper, but I was very fascinated by that paper, but really I wanted to read that sometime, but really because that is where he defines all this alpha and mutual information, etc. Because so one thing, yeah.
And he actually even describes problems where these occur in
Yeah,
operational
exactly.
quantities.
Yeah, that is the good thing about Cesar. He doesn't study anything that doesn't have some operational meaning to that, or at least he tries to find something. Okay, so as far as I know from Cesar's works, so yeah, he certainly he gives an operational meaning to. In fact, he gives an operational meaning to Renyi divergence, Renyi entropy and Renyi divergence of order alpha. Okay, so in that paper. So the title is something like a generalized cutoff rates and information measures, something like that.
So
Or
I may be wrong, but yeah, I think this typically comes up pretty often in channel coding exponents, error exponents.
Yeah, that's
even in the
and
classical problems, is it?
Yeah, in the classical problems as well.
because that trick of raising rho, right, looks like the
Yeah,
sphere packing
exactly.
bound that Gallagher, that trick possibly
Exactly.
could.
So
Just
that
the 1/1 plus rho. Yeah, seems like
and
that's
I
good point.
think I mean I don't remember this exactly, but the Renyi divergence somehow comes up in mismatched decoding where you don't know the exact channel, but there is something else. I could be wrong. But,
explains the title like generalized cutoff rates.
yeah.
Yeah.
I'm sorry. So, what do you mean? Why the cutoff is helpful here? I mean, what do I think? This was Prasad. So, what did you mean by cutoff exactly?
No, I think there is a this cutoff rate and this error exponents are somewhat closely related, is what I remember.
Oh,
Yes.
Oh, you're saying that rate, R cutoff rate, or something, that appears as a parameter there in the exponent.
Right.
Oh, okay. Thanks. Yeah, that's helpful.
Maybe it has some significance in polar codes also, because as I remember, Arikan, when he was talking about polar codes, he said that the story of polar codes starts with this cutoff rates and
Yeah, in fact, he may also mentioned that he got into this through guessing. I mean, so guessing was one step which led him to polar codes.
Right.
Oh, is it?
Yes.
Oh.
That's interesting.
Yeah, so that's what he said. All of that, I mean, even the guessing work was not in isolation. It was, I mean, he had a grand agenda behind everything.
No, I think this happened.
What? Yes.
It was a happy coincidence, I think.
Yeah.
That's nice. Okay, is there any other question for Ashok? Okay, I guess, Shashank, do you have any other question?
No, not really.
Okay.
Yeah. So I'll anyway stop the live stream. We can.
Sure. Actually, let me just thank Ashok for the talk, and then maybe. Yeah. So, yeah, thanks Ashok. Thanks for a fantastic talk. I think the nice part was you really kind of discussed three very different looking problems and put them all together under one framework. So thanks for that.
Yeah,
I
thank
think
you much
just based on the amount of questions, I'm sure it was well received. So thank you very much.
Thank you very much for you too.
And so everyone, thank you for joining. So the next talk will be on a very current topic. It's going to be on COVID-19. Actually, I could not help but notice while Ashok was talking about the task partitioning problems, the two tasks that he talked about were very current in COVID times. I think one was cutting hair and the other one was doing the dishes. That is very so we could all appreciate that. But yeah, so thanks. So yeah, we'll have it mid-September. So look forward to seeing most of you there. It's going to be on COVID. So one of our many of you would know him. It's a talk by Birenjit on his COVID research in the recent times. Okay, so thank you all. Look forward to seeing you.